welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge.
Hi there, my name is Pavel. I'm the host of the House of ZK Radio. Today I'm joined with our guest, Alan, the CTO of Brevis. So today we'll be talking about Pico, which is Brevis's initiative for a zkVM. We will be going over the design decisions, philosophies, and overall, why the direction of a new zkVM. Alan, can you give us a little bit of an intro to yourself and explain why, what made you come into the space?
Yeah, thank you very much for the question. I'm very glad to be here. My name is Alan from Brevis. I'm actually holding a PhD degree in AI, so I was actually previously doing some research in AI field. But when I was seeing this new field called ZKML, I got in contact with some intersections between like Web3, ZK field as well as the AI. I think this might be something interesting. And then at that time, Brevis is also doing something that is related to the ZKML. That is where I joined and then develop a new protocol that is called SPA-ZK that actually accelerates the existing ZKML solutions by more than 100 times. And then after that, I was with Brevis to further extend the ZK landscape to dive into this zkVM that we just announced like 2 weeks ago called Pico. It's a modular and performant zkVM that can handle like pretty complex computations and then do it very fast and efficient. Yeah. So yeah.
Amazing, yeah. And stemming off that, modular and performant zkVM, can you explore like what does modular and performant mean in this context?
Yeah, sure. So modular and performant. So I will go with the modular first, because many things are related to the zkVM design. Many of them are actually monolithic, which means like they are as a whole. You cannot actually change some part of them, or otherwise like you are going to be revising all of them, right? So we want to make it to be modular means that people are kind of easy to actually switch things back and forth using the best things that is best for their applications. So like we have been collaborating with many companies in this field, from our start. So we are actually pretty application oriented, right? And then, but then different applications may have different needs, right? So which is why like we need to be more and more modular to actually take into like different applications into our system, and then to do the fast approving for all of them. So. So for the zkVM being modular means that we are able to, in our case, we are able to switch back and forth different approving backends. So I think we are the first zkVM to actually support that kind of feature around the world. So we are actually now supporting this Stark on Baby Bear, Stark on Koala Bear, as well as Circle Stark on Merson 31, which is a great theory that is proposed just last year. So they actually have different trade-offs. For example, we actually figure out that the koala bear is actually superior compared to baby bear under certain circumstances, especially when the model or the zkVM is actually doing some kind of recursion and it's very heavy recursion. Then koala bear is having a great advantage compared to the baby bear, which is actually widely used by many other zkVMs for now. And then this is one thing that we can easily switch back and forth different approving backends for different applications, so that people can just switch them with just one line of code and then find the best approving backends for their applications. So I think this is one thing. The other thing is like we focus more on this extensibility as well as the flexibility. So by extensibility, we mean that we are actually implementing this so-called glue and coprocessor architecture that is mentioned by Vitalik not long ago, which means like our zkVM is working as the glue point which handles the general logic or general business logic. Well, for other kind of coprocessors, they are handling that is something that is very specific, but it's also very heavy computational logics. Because Brevis already have its ZK coprocessor before, so it is kind of like natural for us to have both of the ZK coprocessor and the zkVM in the same place, and then try to combine and integrate them together. So previously, all the zkVMs are actually having this architecture that built upon the RISC-V ISA, and then upon that they have included multiple functional ZK coprocessors, or also known as precompiled chips. And then this is all the things they have been doing. They have been doing great. But the thing is, for sometimes, as once again, we are very application oriented. For some of the applications, they need very specific circuits that could be applied into their applications. And if you are just going to be doing that with just a plain VM, it's not going to be very efficient nor cheap. So what we do here is to allow the Pico to be easily integrated with these kind of ZK coprocessors. These can be the Brevis data coprocessor that assures the data access, data integrity of different applications. It can also be any kind of ZK coprocessors, like say ZKML, to verify the model integrity, or some other kind of application-specific ZK coprocessors. So I think this is something we also mean as modular, because you are actually adding and switching different modules in terms of either VM or ZK coprocessors, and integrating them together to make it more application specific, and that is good for the specific applications. So this is the extensibility. And then also the last thing is about the flexibility, because for many of the current zkVMs or any other circuits, they are having a very fixed proving workflow. So by proving workflow, I mean that from the workflow that is starting from the RISC-V program to an on-chain verifiable proof. So this is a long process. It has different steps, and then we actually made it the way that you are able to customize the whole proving workflow by constructing the so-called prover chain that is invented by our team. So basically, you can switch back and forth some of the modules or some of the phases inside the whole proving workflow to make it more application specific. For example, sometimes as we are supporting a continuation, we are bumping into many long programs that need to be chunked into different chunks and then prove them one by one and combine them together. But sometimes for some of the applications, they may have a small trace, small program, so that we don't really have to do the chunking, we don't really have to do the combining phase, but rather we just prove it and then recursively prove it until it goes on chain. So in this case, people can just eliminate some of the phases in our program workflow, and then construct their own workflow that is best fit for their applications. Yep. Many aspects.
I like the direction to target the application and the application needs. Some applications have bigger traces, and as a result, you need to have these more sophisticated workflows. And then some applications, utilize some form of a recursion, which you pick based on the application picks the solution based on its needs. And so your goal is to create these solutions which offer the best performance and flexibility for the individual projects that are coming in and trying to use a zkVM. So it's a zkVM that fits this specific use case, rather than the opinionated approach of what zkVMs right now think that use cases might tend towards this, so therefore they're going to optimize this, but in reality it might be something completely different. So you want to adopt those use cases to come on board and create these specific performance and enhancements through that flexible architecture.
Exactly. And so maybe I can mention a little bit about our whole process of having this Pico. The thought process of that. We do that for a reason, because previously we are doing the ZK coprocessor, right? As I mentioned to you, this ZK coprocessor allows all the contracts or all the projects to actually access the on-chain data trustlessly. So basically, what happens is that they have like some kind of data access request and send it to our coprocessor, and our coprocessor will actually send back the data as well as the ZK proof together, so that they can just verify the proof and access the data. Right, and then so this is the ZK coprocessor. We have already collaborated with many DeFi projects as well as many projects in other sectors to actually make it happen, and they are very happy with that because it's super efficient. You can build just our ZK coprocessor as a bunch of like handwritten application-specific circuits that is very efficient to be deployed and used. So the next thing is that how do we deal with this data, right? So there might be some very complex, there might be some simple logic to deal with data. For example, we just take the summation, take the average, these kind of things, happens a lot. But there are also some specific cases where you want to do more complicated data processing procedure. For example, you want to apply an AI model. That is where I bumped into this ZKML world and try to develop the 6-spot ZK framework, where it actually leverages the sparsity that is everywhere in the model, and then can accelerate the whole ZKML procedure. So you can also view it as some sort of ZK coprocessor, but in the AI field. All right, but then like we realized that as we have been collaborating with many of the DeFi projects, we gradually realized that okay, the ZK coprocessor or the logics that we want to encode into the circuit actually goes way beyond just the data access, right? There might be many other logics that we want to encode into the ZK circuits. For example, as I mentioned, like AI things, or like we have just talked about Ethereum blocking, Ethereum block proving, right? We just prove each of the block execution and then send the proof to the Ethereum, instead of just doing the EVM execution on chain, right? So this is also something that we want to do. So you can see that this kind of general logic actually requires us to have some kind of solution that goes beyond merely the ZK coprocessor, and that is why like we come into the Pico or the zkVM solution, where it is the most flexible way, and then it is able to integrate with many ZK coprocessors together to actually achieve these application-specific things. Yeah.
Awesome. Yeah. And with this, you also have performance, the results essentially.
Yes.
By my notes, you have around 70 to 155 times faster, or sorry, 155% faster than RISC-0, SP1, and OpenVM. So, in terms of this, what kind of benchmarking are you using? What type of strategies are you using? And because those are really large performance gains over what we think, where we think like the standards for zkVMs are. So how are you accomplishing, let's say that within the benchmarking?
Sure. So speaking of the benchmarking, I think this is a pretty complicated topic in this field of zkVM, because you can see every day that each zkVM is having their own benchmarking criterion, own benchmarking methods or something like that. So in our benchmarking results that you have just mentioned, like we are able to achieve like more than 70% of percent faster compared to the second best among all of us. In that case, like we are benchmarking specifically on a CPU. So everyone is on CPU, and everyone that runs are without any kind of compiler optimization or optimize the parameters. So what we do here is to just run their plain code in their code base, and then with their default parameters. And this actually applies to Pico as well. Right, so we are trying to do exactly the apple-to-apple comparison in that sense. So they are running on the same hardware, they are running with the default parameters and then no compiler optimization. And then in that case, like we can see how they actually differentiate with each other in terms of like a better architecture or something like that. And then we are also like thinking of like different benchmarking workloads, right? Because there are many diverse, I mean, this field is so diverse, there are many things that you can benchmarking over. So we chose like both those like a very artificial and then smaller programs like a Fibonacci with the input of 300K. So this is like a pretty small program that you can just prove within like tens of seconds, or those larger proofs like proving the execution of say Ethereum block or the tenement light client. So these are the more realistic real-world cases that we have been benchmarking on. And then what we also did is that we try to align each of them running exactly the same program, because like sometimes different zkVM teams may develop their specific program for the same problem, to solve the same problem, right? And then what you do is to gonna be recompile these different programs, and then of course it will result in different RISC-V instructions, and then you cannot see if one is better than the other, why it is the case, whether it is because of the program that you write in a good way, or it's just because that your architecture or your some other things that is playing a role here. So we try to do our best to use exactly the same program that they developed, or some of the time that we developed for them, to run the benchmarking, and then there comes a result that we are at least more than 70% faster compared to all the other cases. And then so this is one thing. This is one way of the benchmarking. So we just allow every single one to use exactly the same setting to make exactly an apple-to-apple comparison. This is also the thing that we have reported in our blogs. But we also have done it in another way that is kind of interesting, because we actually realize or recognize that the different zkVM teams have different best setting or optimal settings for their own zkVMs, right? So that's why you can see that different teams have their own repo of benchmarking, and then these own repo have written different benchmarking codes for themselves. Some are using some compiler optimization, some are using some optimized parameters, and then we can also do it for Pico as well, right? So, and then this is something more realistic, because although we are still working on the same hardware, we can leverage each of the strength of each zkVM to make them the best performer, better performant compared to what they originally have. So we actually also did that, and we also open source that. It's called a zkVM zkVM bench, so that you can just check online and run it yourself. What we do here is to say that we pick the corresponding benchmarking repo for each of the zkVM. For example, SP1, we take their zkVM perf and then run directly with their settings. For say OpenVM, we take their OpenVM Wraith benchmark and run with it under their setting. And we have our own setting. We have optimized for the compiler, all these kind of things as well. Some of them are the same as theirs. Some of them are different, because we may have different optimal settings. And in this case, we are still getting kind of similar results. We are still faster compared to the second best one, and by a large gap. So yeah, I think this is something that we also want to, we also did, and then I think it's more realistic. And then I think there's a third phase that we're gonna do, is to say we do on their optimal hardware, right? Because now we are using exactly the same hardware. And then I think this is the best way to actually review that which architecture is actually the best. But at the same time, some of them have GPU implementation, and some of them don't, right? We are implementing our GPU version as well. So hopefully after that, we can also benchmark on on the optimal hardware that is optimal for each of the zkVM as well. So please stay tuned to that.
Awesome. Yeah. I like how you prioritize the apples to apples and make it so that you're using their what they released, what they're testing off of, and then essentially taking the same types of methods, like Tendermint consensus, and then Ethereum blocks, and different things related to real world use cases, and sort of just doing the apples to apples, the CPU, making sure that everything is aligned and not manipulated in that way, which is really good. And I guess going back to, so I know you mentioned briefly about the proving workflow for Pico and how it's very modular in terms of the specific use case. Can you go into and explain the process from RISC-V execution to the on-chain verification process?
Sure, no problem. So the whole proving workflow actually runs for, as you have mentioned, it's running from the RISC-V program until the proof that is verified on chain, right? So we basically have divided the whole whole proving workflow into several phases. The first one phase is to basically generate a RISC-V proof from a RISC-V program. And then this is a RISC-V phase. And then after that, we have a convert phase, which actually converts the original RISC-V program, RISC-V proof into a recursion proof. So this is one-by-one mapping. And then since we are doing kind of continuation, if we have a very large program, then we basically have them different chunks, and then now we have like several, like say number of n different recurrent proofs, and we want to combine them to one. So this is what we call the combine phase, where we basically do this like n by one, where m is usually taken as 2, and then 2 by 1, 2 by 1, 2 to 1, 2 to 1 combination until we have the final recursion proof that is only one proof. And then after that, there's also some optional things that you can do. For example, currently there's still the proof size is still kind of large, and you can do the compression phase, which actually is taking a more aggressive compression-friendly parameters in Stark to actually compress the size of the proof size into a smaller one. You can also do the embed phase, where it's actually transforming the original field of the proof into a BN254 that is snark friendly. And then finally, we will translate all these kind of proofs into a constant size on-chain verifiable proof. So this is the whole thing. And then zooming a little bit in, there's actually the so-called instance. This is something that we also implemented. So the instance is the smaller VM that is inside each of the phase. So for each of the phase, you have a specific smaller VM that is handling the specific proving logic. So each of the instances comes with its own circuits or chips. It comes with own proving backends as well as proving processes. So basically, you can back to the topic that it is kind of modular, means that you can just switch like different proving process or proving logics inside the instances to actually update the instances, and then you just plug instances into the different phases to actually make the whole proving workflow happen. So you can see that this is like a more like a Lego-like procedure, and then you got just building something up into instances, and then building combining these instances in our prover chain to actually build the whole proving workflow. So we have spent a lot of time to try to make it easier to be used and deployed and tuned as well.
Mm-hmm. And for the customization for the workflow, so I think as far as I'm aware, you're one of the only projects working on that customized work, but I could be wrong. How easy is it to add in those customizations? Do you have like a specialized SDK specifically for that, or is there anything that developers need to know and understand in order to fully take advantage of this optimization?
Yeah. So those are more advanced usage of our VM is basically to do the plug and play and to do the updates of their own proving instances, because in that way you are going to be kind of familiar with the whole proving workflow as well as the proving process within each of the instances, and you have to be very clear about what the thing you are going to be doing next. Right, and then after that, you can actually implement or update the circuits that is inside them. So yeah, so we have we have a whole section that is called exactly called advanced session in our docs. So advanced developers can actually go to that advanced docs to actually see how it is actually working, and then after fully understanding that, they can actually do the manipulation by their own to create their own workflow for their specific applications.
And can you give some examples of some of the workflows that you're currently looking at that are related to real world cases that developers can experience today? Is it I know that you mentioned briefly about the Tendermint consensus verification. You mentioned briefly about Ethereum blocks. You mentioned a little bit about that co-processor point where you're bringing on-chain data that's older than 100 blocks back in. Is there I guess an example that you can give that outlines those performance advantages within the workflow?
Oh yeah, so I think it all depends on what kind of application you're going to be working at, and then what is the specific property that your application having. So as I think, I just mentioned one example that we have been working on is that so these kind of programs or like these kind of the whole execution is usually very small, so they have a higher limit, they have a limit that is not very high. So in this case, we can just implement the whole workflow as if it only has one chunk where the chunk is large enough to hold the whole thing. So in that case, as I mentioned, like originally we have like different chunks that we want to combine them into one. So we need to have this combined phase. But then like now it's only a one chunk, right? There's no need to actually do this extensively. So it's no need. We will just eliminate the combined phase to actually make it more efficient. So something like that. And also for some of the cases, you want the proof to be small enough before it actually goes into embed phase or the EVM phase. So in this case, you can add one more compression phase to actually just compress the original proof that is already small to be smaller, so that it can actually perform even better compared to that. So it also actually you can see that we are actually trading off like between like we have like a very huge trading off space that you can do the manipulations or like do the tweaks to make it happen. So basically, what is your priority? What is your priority in your application? Is it latency? Is it cost? Is it proof sizes? All these kind of things. And then basically having this kind of flexibility allows you to trade off between these kind of factors that is best fit for your application.
Amazing, yeah, and then with the addition of that flexibility, where like you can trade off the speed, the latency, the cost, the size maybe of the proof itself. So like you have different parameters that you're adjusting to then make the application itself more usable, and as a result, create use cases specific to that application's needs. No, that I think is a really big differentiator, especially with zkVMs today, where it's a kind of like a one size fits all solution versus yours is more of like you decide how performant you want your system to be. Yep. and what it's specifically within that problem space. So we mentioned like some use cases that are primarily based on like on-chain actions. Do you see like use cases coming from off-chain interactions? So I know you mentioned like ZKML as one of the use cases, and that you're primarily a specialist in that area. Do you see like any other use cases evolving from like off-chain data access and usage within these systems, or like anything that these systems would like Pico would enable? Essentially, what other use cases could you see this being adopted within the ZK space?
Yeah, I think the two of the most frequent use cases that we have bumped into are exactly two that you have mentioned. The one is the thing that allows the on-chain contracts to actually access the on-chain data trustlessly. I think this is the one main theme that we have been working on and have been collaborating with many big names in this field, in this space. The other one is, of course, the rising field or emerging field is ZKML, because the other day I was attending a ZKML panel on AI agents. I mean, like everyone is like quite excited about the future that AI agents is going to bring. It's not only about, it's not within only within the Web3 circle, but also within the general public, right? People are very interested, and some people are actually anticipating that the year of 2025 is the year of the AI agent, right? So that is where we see that maybe ZKML could actually come into play, and then try to attest the model integrity within the AI agent systems. Because like usually, if you really want your AI agents to work as exactly you need, or at least you want to attest that you are working on or using the model that you are actually requesting. I think this is the thing that you need to, ZKML is probably one of the solutions to that. There's also some hardware solutions, and then ZKML is the software solution. I believe that maybe in the future we will have like a hardware plus software solution. And then I was talking to the other guy like working in this phase, and then using this ZKML to accelerate or to attest their model integrity, just to make sure that they are having.
Yeah. Yeah, no, and I think like technology today, I think like right now we see like TEEs being used by like, Flashbots for that integrity piece. But I think like, as we see ZK, being more performance and like with the assistance of Pico, I think that, we can see more of these software related improvements, and as a result making it more accessible to a larger audience, and not having to rely on this hardware and just on TEEs alone. And I guess for Pico, looking long term, the next, let's say 1 to 2 years, how do you see the developments going towards? Like, where do you see additional improvements or anything related to those?
Yeah, I think there are many things that we are concurrently working on, and it's also very exciting, and especially seeing that it's now Pico is already a version 1.0, and then looking forward into like 1 or 2 years, it could be like a Pico version like a 2.0, 3.0, and all these kind of things. It's very exciting to expect that it can improve a lot, and then several things that we have been working on. First thing is that we have been spending a lot of time to refine the whole architecture. I mean, like we already have a very modular architecture that is kind of easy for both developers to develop the new applications, as well as for us to actually maintain the whole code base, because it's just a modular. It's you know it, right? And then, but we think that it can be done. Yeah, there are many ways to actually also to make it better. So this is something that we have been working on recently. Another thing that we have been intensively working on is the GPU optimization, because like currently we are just working on the CPU, and CPU is already having a pretty promising results, and which actually gives a lot of confidence, because like we believe the current architecture, as well as some of the key insights or key designs in our CPU implementation can actually transfer into the GPU implementation, and then we will expect the current margin will actually maintain or even be amplified during our transition to more powerful GPU clusters or something. So yeah, this is something that we have been working on. We believe this is not far away right now. And then third thing would be to think about more applications, as well as integrate more ZK coprocessors, because we do think that this is the way to actually make the mass adoption of ZK. Because like now you can handle general circuits with ZKML, zkVM. Well, you can handle application-specific circuits with your own ZK coprocessor. And then for any kind of application that shares some kind of complex computation, we can develop a ZK coprocessor for them, since we already have the experience with developing that. And then for those more general cases, we can just use a zkVM to handle that. So it's very exciting to see that the combination or the glue and the coprocessor architecture can play a role in this space. And hopefully we can see more and more application that is adopting our solution as their default ZK solution.
Amazing. Good on the developments. Good on the direction. I like the glue and the coprocessor model. I think that's the direction that will lead to the best involvement from many different use cases. You focus on what the application needs, and then and then the application decides then what Lego pieces to then adopt to get their solution off the ground. And I'm glad that you're creating this vision to help that adoption through that technology. Thank you so much, Alan, for your time, and yeah.
Thank you very much for hosting.
Curious to hear more about the future developments.
Yeah, I'm looking forward as well. Yeah.
Awesome.
Thank you.
Thank you.